might not look like it, but this is a factory belonging to the 200-year-old German family firm of Faber-Castell. In the basement of an old castle in what looks like a gremlin's kitchen, master pencil makers like Lothar Borgerdine mix up batch after batch of pencil lead mix. The recipe involves mixing graphite with china clay. Just add water and set the blender.
It's like being a chef. You've got to get the mix of ingredients just right.
From the blender to the oven, the lead making process continues. Forced through an extruder, the graphite takes on a recognizable shape. But although these may look like pencil leads, they don't behave like them. Before they can do their job, these unfinished leads still require baking and cooling. Until then, the leads are as bendable as rubber bands. After the oven comes the deep fryer. Leads are submerged in a bath of molten wax and oil. The more wax in the mix, the harder the pencil. Faber-Castell has come up with no less than 16 degrees of hardness, each defining a different level of the pencil's blackness. The graphite ore has been turned into pencil lead. But how do they get the lead into the pencil? The process starts with these wooden slats. Each one is 18 centimeters long and 7 centimeters wide. At a phenomenal speed, a router cuts a sequence of grooves into each slat, one slat every second. What follows is a kind of sandwich making. First, the grooves are striped with glue. Then the conveyor belt divides, and the graphite leads are laid into the bottom row of the grooved slats. The slats are then glued together top and bottom with the leads inside them to form a basic pencil template. The newly made sandwiches then stack themselves horizontally onto a giant cylinder-like rotisserie. This slowly revolves over 90 minutes inside a big oven to cook the glue. If the glue does its job, the slats will bond into one solid piece of wood with no visible join. Gluing the slats properly is the secret to how they get the lead into pencils. As a new slat stack enters the rotisserie, so a cooked stack is pushed onto a conveyor, which feeds it into another router. This is the machine that actually cuts the pencil shapes from the slats. There's very little waste. Each pair of glued slats will yield as many as 10 pencils. The pencil is made, but it's hardly finished. To stand up to the rigors of daily life, it needs a protective coating. And that presents a problem. People don't just write with pencils, they also chew them. The scientists working in Faber-Castell's lab faced a real conundrum: how to find a chew-proof coating. Paint would flake, plastic would peel. Eventually, the scientists came up with the answer: a water-based varnish. Standard varnish is spirit-based. It's toxic, but the pencil varnish is completely safe. Varnishing the pencils involves building up over 5 coats into the final color. The varnish needs to be tough, not only resisting the chomping of human teeth, but also resisting a much more destructive power: human sweat. Sweat is the pencil's biggest enemy. To simulate the humidity and corrosion that a pencil is likely to face in a lifetime of human contact, scientists at Faber-Castell use a form of synthetic sweat. They call it the sweat test. Pencils are bundled together in an artificial perspiration environment and left for days. Scientists spin the pencils 10,000 times, the equivalent of passing through hundreds of hands over a period of years. If the pencils get through this, they can handle anything that we throw at them. These pencils have passed the sweat test with flying colours, all because of the varnish that coats them. After branding, sanders shape the front into a distinctive point. Before our eyes, a pencil is born. Like a concert pianist, the fingers of a quality controller dance across the pencils like piano keys. Instead of B flat, she's hunting for 2B, 4B, and HB. It's a different tune, but the scale is just as demanding. Since this program began, the world has produced nearly 500,000 pencils, enough to stretch 90 kilometers. In the hands of an artist, a storyteller, a scientist, a designer, the pencil has limitless potential. 5 ordinary objects, 5 extraordinary stories. Coming up, we each get through 400 litres of it a day. Without it, we would soon die. Yet as we turn on a tap or shower, how many of us give it a second thought? The secrets behind water supply. Next, on How Do They Do It? Tommy Johnson's family has been in the drilling business for 3 generations. Today, Johnson is working a few kilometers outside the city of San Antonio, Texas. As a Texan, you might think he's an oil man, but in fact, he's drilling for a natural resource far more precious. Water. It's a nail-biting job.
A water well is not worth 15 cents until you get water to come out of it. And the water's in the very bottom.
The people of San Antonio depend on drillers like Johnson for their very survival. Because in common with 20% of the world's population, San Antonio gets its water from a source deep underground. It's called an aquifer. Johnson's drill head is biting through the tough Texan soil in a bid to reach one of America's largest underground reservoirs, the Edwards Aquifer. The Edwards is a massive cave system that descends as far as 1,000 meters below ground. Tiny conduits give way to cathedral-like, stalagmite-encrusted chambers. Edwards is bigger than the entire US state of Connecticut, and it contains countless billions of gallons. Indeed, there's so much water that in some places you only have to stick a pipe in the ground to release a raging torrent. But don't let this image of plenty fool you. Getting the water up to the surface and making sure the aquifer doesn't run dry is a major operation involving a dedicated team of engineers, geologists, and hydrologists. So how do they do it? The story starts with rain. When it rains in southern Texas, it really rains. And because of the region's geography, much of this rain quickly finds its way deep underground. High on the Edwards Plateau above the city, hydrogeologists Gary Schindel and George Venny are hunting for gateways to the aquifer. The Edwards Plateau is made of limestone, a rock that's porous to water. If you look carefully, you can see that the ground is riddled with fissures and caves, all carved by the rain.
It's important to map the openings, these conduits, these caves in the aquifer, to understand how it works.
Mapping the exact route of the water once it enters the cave system is vital for keeping a check on